Hi, my name is Octavian, and it's 12 sharp. And you know what time it is? Lab time. Today, we're going to examine some oxidant and reductant properties of some substances. The most available substance which can play the role of oxidant should be the potassium permanganate, which can be purchased from a drugstore. The other substance that will play the role as a reductant will be the hydrogen peroxide. Mine hydrogen peroxide is 35% concentration, but you can easily purchase one from the drugstore, but there is only with 3%. According to the conditions of the reactions, hydrogen peroxide can be either a reductant such as oxidant. If we want it to be a reductant, it should give electrons, and if we want to make it an oxidant, we need to give them two electrons. Give it two electrons, so it will form H2O. Okay, and the O2 gas is for the reductant. First of all, we are going to examine the reductant properties of the hydrogen peroxide. We are going to add hydrogen peroxide to potassium permanganate to observe an interesting thing. Okay, so in this test tube I have potassium permanganate, and here is my hydrogen peroxide. So I'll add them both. Look at that. It's like a cloud. What a beautiful thing to look at. Look at this. Wow. Okay, let's not play with it. So, wow, the amount of heat eliminated is just enormous. Okay, so the next thing I should do, and then I'll explain the processes, I'll demonstrate that there is indeed the oxygen gas. So I will take some matches. Okay, I will demonstrate that there is oxygen. Then a splint is lit and allowed to burn for a few seconds, then blown by mouth or shaking. Okay, let's blow it. Okay, and add it. Oh, the effect wasn't so good. Okay, I'll try it, but with another portion of oxygen. Okay, let's have, and the amber is from the tip of the splint is lit. Okay, look at this. Look at this effect. Okay, look at this. Do you see it? The oxygen is causing that. Okay. Yeah, that's interesting, but let's explain them in the process of chemical equation. It of course was a redox equation, so potassium permanganate in a solid form plus hydrogen peroxide resulted. The potassium hydroxide plus the manganese dioxide, which is a precipitate. This is aqueous, it's a solution. It's solid, plus O2, that is the gas, and plus water. Of course, the enthalpy was lower than 0. Okay, so then we see that the manganese have its oxidation state of +7, and here it has +4. It changed from +7 to +4, and the oxygen from it's plus, so this is minus, from -1, it changed to 0. Okay, let's write that down. 2 oxygen with minus to turn into O2 only. 0. Okay, so in order to that to happen, it needs to give 2 electrons. 2 electrons. The manganese with +7. Changed to manganese +4. So in order to that happen, it needs to addition +3 electrons. Okay, so of course this one was a reductant and became an oxidant. This one was an oxidant and became a reductant. It is an oxidation process. It's a reduction process. Okay, the lowest multiple, a common multiple, is 6. So 6 divided by 2 is 3. 6 divided by 3 is 2. Okay, now let's proceed to the equations. Okay, so we need here 3. And here we need 2. Okay, the potassium needs to be equaled. It's 2. The manganese 2 is 2. Okay, so we need here 3. Yeah, of course 3. And we need to equal the water. So the amount of hydrogen here is 2, and there are 2. Okay, there are 6. Okay, 4, 6. We need here 2. Add 2. Yeah, and the equation is balanced. Okay, so where do I know from that the oxygen is heavier and it will remain in the test tube? So there is a formula for this. If we speak about the formula of the ideal gas, that's PV equals to M on MRT. We can easily say that M is equal to the volume multiplied by its density. So PV equals to volume multiplied by its density on the molecular mass of the gas and multiplied by RT. Okay, we will multiply both with 1 over V and here 1 over V. Okay, so V this and V this will cancel them out. So we will obtain that P equals to rho on M and multiplied by RT. Where R is a constant, T is the temperature, and P is the pressure, and M is the molecular mass. This one is the density. So we should obtain that the density is equal to P over RT and multiplied by M. So the thing is, I want this one to call a constant, because if we do not change the conditions, we do not change the pressure, and we do not change the temperature, it should remain constant if we compare two densities. So this one, I will say that it's equal to A. In order for that, the rho, the density, is equal to this one, A, multiplied by the molecular mass. So if we compare two gases on with the same in the same conditions, we do not change the pressure and we do not change the temperature, the density is directly proportional to the molecular mass of the gas. So we should say that the density of the oxygen on the density of the air is equal to, okay, A A and multiplied by the molecular mass of oxygen on A multiplied by molecular mass of air. Okay, so we can see that these two will cancel them out. So it is equal to the molecular mass of oxygen on the molecular mass of air. And from the periodic table we can find that the molecular mass of oxygen is 32, and the molecular mass of air, we consider it is known, I found it online, it's equal to 29. So it's 32 and 29. So we can see that the density of O2 is higher than the density, it's bigger than the density of the air. And as you know, it is quite a simple example. That example that can give the vase, and here is the water, and on the water you will pour some oil, so the oil will float on top of the water because the oil is less denser. So the more denser will stay at the bottom and the less denser will escape the our vase, our chemical vase. The wood consists almost 50% of cellulose, so I will write the equation down for the burning of the cellulose, because besides the cellulose there are other organic compounds that there are so many I just cannot explain them all. I will not have enough space for this. Okay, the cellulose has the formula C6H10O5, and it is a polymer, so we'll write it as N times plus oxygen gas at temperature, of course. To ignite it, it will equal to CO2 plus H2O. That is the water. Okay, and of course this is the enthalpy is lower than 0. Okay, now let's see. This one is plus, this one is -2, so this oxidation, he has the oxidation state of 0. Now here he has +4. There is 0 and there is -2. So we'll consider the equation. C6, it's 6 here and N here, so 6N C, C that has 6N, of course, and here is 4 plus 4. Okay, oxidation state. Then in order for that to happen, there is 0. In order for that to happen, it needs to give 24 N electrons, because this N, we do not know what's this, 24 N electrons. Okay, then the oxygen, O2, changes to 2O minus 2, so it needs 4 plus 4 electrons. It's 4 here. Okay, then the this one is a reductant, and it became an oxidant. This one is an oxidant and became a reductant. This one is called a reduction process. This one is called an oxidation process. Okay, so the lowest common multiple is 24N. Okay, 24N divided by 24N, it's 1. And 24N divided by 4, it's 6N. So we should have 6N here, 6N here, and how many molecules of H2O. So 10, there are 10 and 5. 10, it's H2O at the 5 times, and with the N, it's 5N. Okay, it's 5N. And the equation is equaled. Next, we will proceed to the next experiment that someone would recognize it as the elephant toothpaste. So, I have here a solution of soap. It's just regular soap. Then, here I'll take some hydrogen peroxide and add to the soap. Nothing will happen. Then I'll pour some potassium permanganate on this solution, and we will see the reaction happen. Safety glove first. So, yeah, let's begin. Look at that. So, what's the trick here? It's really interesting. It's a really interesting equation. It's this equation that I have just explained, but the oxygen was bubbling so much that it made all the soap, the dish soap, it made to make a lot of foam. So there is nothing interesting besides the fact that there is a lot of oxygen emitted, and the soap made the foam. Okay, that's it. Next we will proceed to understand the oxidation properties of the hydrogen peroxide. So I would honestly like to tell you that this one was one of my first experiments ever made. It was something 4 years ago. Yeah, it was my first, but proceeding to the next one. So here I have prepared a solution of potassium hydroxide and a solution of chromium chloride 3. I'll add hydrogen peroxide to the potassium hydroxide. Okay. And drop by drop, I will add chromium chloride to it. Okay, it starts to react. Okay, let's add more. Okay, we apparently see that it is green, but it has turned yellow, and that's very interesting. So from the green it turns yellow, and in a second I'll explain that reaction. So the equation for this process is potassium hydroxide in this aqueous form or solution form plus chromium chloride 3 and plus hydrogen peroxide is equal to potassium dichromate plus water. Nothing else but water. Okay, this is a solution, this is liquid, this is a solution, aqueous, and this one is liquid. Of course, the enthalpy of formation is lower than 0 because it's an exothermic equation. And okay, so we see that the chromium had +3 oxidation state and the oxygen had -1, but then suddenly changed that chromium had +6. Okay, it's +6 because we know there is -2 multiplied by 4, it's -8, and +1 plus 2, it's minus 6, so it should be plus 6. And the oxygen changed to minus 2. Okay, so chromium, there is one, chromium, chromium, from the plus 3, it changed to plus 6. So in addition to that, it needs to give 3 electrons. And the oxygen, to oxygen of minus 1, changed to oxygen of minus 2. In order for that, they need to addition 2 more electrons. This one was a reductant, this one reductant, this one is an oxidant, this one was an oxidant, and it became a reductant. Okay, so the process is known as oxidation process, and this one is a reduction process. The lowest common multiple is 6. 6 divided by 3 is 2, and 6 divided by 2 is 3. Okay, we'll proceed with the chromium. So chromium, we need to add 2. 2 here, and of course 2 here. Okay then. Oh, and oh, honestly, I've really forgotten. It's plus potassium chloride 2, of course. Okay, then chloride 6 here. 2, it's 4 plus 6 is 10 here. Okay, so we have 10 here. So we add 3 here, of course, because our redox equation. And we need here, how much? How many hydrogen? 10 plus 6, 16, it's 8. Okay, it's 8. And the oxygen should be equal to, it's 4, 8 plus 8, 16. Okay, 10 here and 6, yeah, it's equal. Okay, so the solution turned yellow. From the greenish color of the chromium chloride 3, it turned into yellow. That's due to the presence of the ions of chromium 04 minus 2. So thanks for watching and have a nice day. Bye.